handout. But again, do not, for this lesson, do not rely on the handout which I have given to you. Just focus very carefully the thing which I'm just going to do that for you on the board. Because the lesson that you have here, I have to add so many stuff to this to make it more general in order not to have you memorize many stuff, which also is a conclusion and towards the end of this chapter. Then, I'm going to teach you how to derive the things from a general format. Then you do not see them in the content of the advanced function. Then you have to exactly listen to the things which I'm just going to do that for you and write it on the board. Then it means that if you get tempted to talk to someone who's next to you, then it means it's so bad. Then you are just going to miss pretty much of the content. And the second thing which I'm going to tell you is this. Most of the stuff I'm going to cover today, it essentially plays a kind of a good background for your calculus that you're going to get next year, level 5. Then please try to learn everything, because next year also your life is going to be much, much easier. Now, let's get started then. We have reciprocal of linear functions. It's specifically, this is the lesson, is specifically focused on the concepts of the linear function, but I'm going to teach you in a general format. You do not have to memorize the things. You are able to, at the end of the session, you will be able to derive the formula and the conclusions. Yes? Yes, please. Now, look at this. The first starting point is that I'm just going to essentially start by remembering the things that we did before. And it's essentially, the first few minutes is going to be a kind of easy stuff. Do not get bored. Look at this. For example, we start by the linear, then we expand it to polynomials, more general format. Look at this one. The first function that we see on the board, to us, seems a very normal function. You look at it, it behaves quite normally, because even if you try to plot it, you say that, okay, I'm interested to plot this function, then when you plot it, you see that it's a completely natural function. Y equals 2x minus 4. We start, as I said, by a linear function. We say, oh, this function is quite a boring function, because when I look at this, based on the things which we learned in the prior year's math, I noticed that this function behaves like a function that its domain is always a real number, and its range also is always a real number. Nothing very specific and interesting about this. Everything is normal. It's a boring behavior. Along the way, imagine that if, for example, Michelle is climbing the function, she starts from walking here. Along the way, everything is going to be normal. Nothing interesting. But now, Michelle comes here and say that, okay, I want to pinch this function. What happens? It flips the function, and we say that y equals to 1 over 2x minus 4. Now, we can flip the function. Essentially, what this is the context of the book is that this is called the reciprocal function, because you bring whatever is at the denominator, you bring it up to the numerator, and whatever is at the numerator, you bring it down, and you get to this function. Now, things are going to get a little bit, I should say, crazy. This function, Alexandra, is not going to behave as what we expect a normal function as a linear function does. From, I should say, the math, at level 11, math level 3, you remember that this type of function represents what? A rational expression. When you have a rational expression, the first thing which grabs your attention is what? At this stage, you look at the basement I always call the denominator like the basement. And I say, okay, I look at the basement here, and what I look at it is that I have to be careful. For example, when you have a basement, you are always careful that your basement doesn't get into the fire. Now, and that's what we does with this kind of, I should say, function. We say that our fire is this, that our denominator tends to become 0. Yes, Irish? We say that in that case, what happens if 2x minus 4 becomes 0? If the denominator becomes 0, you have learned it from level 3 math that you say that x is going to be 2x equals 4, then x is x equal to 2. What we have learned from level 3, hi Russell, how are you?
Good.
Awesome. Oh, Kevin, Calvin, not Russell. I had a meeting. So, no problem, no worries. Everything is good. Look at this. Now, we say that when we imagine that if we solve, let me just give you a handout, Calvin. There we go. But do not rely on that. Focus on the thing that we do on the board. It's just like a roadmap, but it's not all the thing that we need. Then we say that this number is for us, which is the root of our basement. We call this what when we were level 3? Restriction, huh? Or essentially we're going to call it from now on the singular points, because you see that also when you go to the calculus, you're just going to call these one singular points. Singular points. We got the singular points by taking the denominator goes to 0. Now, and we always make sure that when we are there, the domain of this function, we say that the domain of function is essentially all the x's that are real, however x cannot be equal to 2. Because if x becomes 2, essentially that's how you have the basement of your house set to fire, and that's the disaster. Now, I'm just going to look at this. When life gives you lemon, what do? Make lemonade. Make lemonade. That's right, Alexandra. Thank you. And now, when you have a trouble in the basement of your house, and x cannot be 2, then make the lemonade. Again, make sure to watch the video now. Then, when the light has given you a lemon, and now you have x equal to 2, and it means that all the house is burned down, it means that now you do not start to cry. Now you enjoy, you say, oh, I'm just going to make the lemonade of the disaster which just happened. What does it mean? I plotted this function over here. I'm just going to plot this. You can also use the Desmos that you can see their resolution of the things that we are going to do. Look at this. We say that x equal to 2. I'm just going to highlight this on the x-axis, which I have here. X equal to 2 is this. For example, this is plus 2. And I'm just going to, with this color, highlight this. Now, yes?
Why did you put it 1 over the function?
I said that, imagine that you flip the function, you put the numerator on the denominator. That's because that you reciprocate the function.
Oh, yeah, got it.
You reciprocate the function. You take the one which is on the roof that it falls at the basement. And that's what we did. We call it reciprocating a function.
Yeah. There was a denominator already, and you flipped it with the denominator come to the numerator.
Yes, because you say that if that's this, imagine the denominator is 1.
Oh, but if it was like 4, for example, that would be 4 over.
Yeah. Anything. Even if this is 4,
yeah.
Any number it goes up, this one goes down.
Okay.
We call it reciprocating the function. Now, look at this. Now, as Alexandra said, now that I have this lemon, Alexandra, now that we have this disaster, when I plot this function, I see a very strange behavior. The blue line is essentially the thing that this is going to be the function of f of x equals to 1 over 2x minus 4. That's the blue line. Now, look at what has happened now. That's the time that now we are just going to make the lemonade x, and this is the point equal to 2. Now, look at this. What's going to happen right now? Before I move on, I say that, okay, the point which caused the fire in the basement, which I always used to avoid it, when you were doing functional level 3, you always just went, when you had a rational expression, you always went, okay, the denominator, that's the denominator, let's set it to 0, then find the roots, then I call it the restriction for singular points. Now, at function level 4, and when you go to the calculus, we use this as a lemonade. I'm just going to plot that number, x equal to 2, is this orange colored line. I call this one. Is this function vertical or horizontal? The orange line. Is it vertical or horizontal? That's right, vertical. Then I'm just going to call that vertical asymptote. Vertical asymptote. That's what we call this. But let's explore what do we mean by it. Okay, for the vertical asymptote is this. We say that the root of the denominator becomes my vertical asymptote. Now, what do we mean by the vertical asymptote? Look at the point which is x equal to 2, which is going to be my vertical line. And also the function which I have there. Anybody knows what do we mean by an asymptote? Or when you go higher, when you go to the calculus, when you go to an engineering program, you always look for the asymptotic behavior. But what do we mean when we talk about asymptotic behavior? Anybody can define it for me? You're going to take that definition all the way when you graduate from university. Yes.
It's just that, like, and the function can get closer and closer to that value. That's it.
That's so true. That's what we mean. But look at this. What essential next said is this. Imagine that. For example, Lauren, one day you like to drive, you love driving, huh? Imagine that. For example, this is there is a car. This is Lauren driving it, and also Angelique also. She's also driving a car, which is alone. This is Lauren. This is Angelique. Let me just put your car in different. Let me put this one here. This is Lauren. And this one also. This is Angelique. Look at this. These two persons are driving their car. Look at this. Angelique is driving along y x equal to 2, and also Lauren is driving along the function which is 1 over 2x minus 4. Driving so fast. Look at this. When they keep driving along these two paths, trajectories, they do not look at this, their car. They are driving fast. They get close as much as they can, but they do not bump into each other to damage the car. And that's what this is called with the asymptotic behavior. The lines and the function, Medina, they are getting as close as possible, but they do not cross. That's what we mean, Michel, by exactly the asymptotic behavior. Now that you know the asymptotic behavior, and then we talked about, I should say, the vertical asymptote, it means that there is a line. Vertically, it's vertical asymptotes with the function. The function and the line, they do not cross. They do not cross each other. Now, then as a result, I say that this vertical asymptote comes with the equation that x is equal to 2. Bye, Nick.
Bye.
Please watch the rest of the video.
Okay, I will.
Thank you. Bye. Now also, any questions so far? No? And now, listen to this part. This part is going to be very interesting. Now that you learned the concepts of the asymptote, look at this. Now, for this part, imagine that I need two volunteers. For example, the first volunteer which I'm going to take is going to be, for example, between Russell, between Calvin and Ash. Imagine that. Here is going to be Ash, and here is going to be Calvin. You are walking along the function. This is Calvin, this is Ash. You are walking along the function, trying to just reach to each other, then shake hands. Look at this, Alexander. When Ash is walking towards the asymptote, he sees that, okay, he keeps walking, keep walking, and he sees that, oh my God, I can never reach Calvin on the other side, because he sees that there is a huge gap between them. Then what do we say, and how do we write it? We say this. We say that instead of verbalizing it, I'm just going to write this notation. I say X, if it represents, for example, the path, that now I'm talking about Ash, then I come to talk about the Calvin. Then I say that if X, Ash is walking towards the X, then I just represent X, and I say that X with the arrow, this arrow means that X is getting close to what number? Plus 2. But listen to this part, it's very important now. X is going to 2, which is the direction that the Ash is moving towards 2, but however, when Ash is looking at this direction, he sees smaller numbers. You see that when you are here, you get 5, then you go to 1, then you're always looking at the smaller numbers. Because if you look at the Ash eye, look at that, this is Ash eye. He's looking that direction towards the way that the X is getting small, then symbolically, I put 1 minus on top. I mean that X, Ash is walking towards 2, but from this direction. However, I have my functions also. 1, which is 2x minus 4. Now, Ash, what do you see? When you walk towards that direction, your plan is this, to reach to Calvin, but it seems that as more you walk towards Calvin, you are getting far away from this. Now you come along the blue line trajectory, you go all the way up there, and nobody knows how long you're just going to walk. We said that in this case, you are going to go to the infinity. Because it doesn't matter, for 2 years you keep walking, you walk along that vertical asymptote, and Lauren, it seems that Ash is walking forever, but never reaches to Calvin. That's what we say. But however, there is something which is missing here. What is this? You say 1 over 2x minus 4 infinity x going to 2 from the right towards the left. I need a symbol that when I look at it, it yells at me. I say, okay, I mean that Ash is never going to reach to that point. At this point, I'm just going to introduce you this notation. You're going to learn that higher years. We call this limit. For example, you say that the limit is, you say that the limit you find, for example, I ask Jaya, for example, what is your limit before you get angry? You say, okay, when there are too much math, I become angry. Then that becomes your limit. Huh? And now that's the limit of this vertical asymptote. We say that the limit of the function, when x goes to its vertical asymptote, from this direction, goes to infinity. And that's what you expect. Ash is walking, he walks along the blue line, keeps walking, you keep walking. And now for the Kelvin. Kelvin is walking again the same trajectory. Your true goal is what? To reach to the Ash and shake hands. You keep walking, Kelvin, you keep walking. Initially everything seems fine, Russell. Everything initially is fine. Ash is walking towards that direction. He sees that also Ash is walking towards him. Seems like, oh my God, I'm just going to meet my friend. But suddenly, when you go towards 2, which is our vertical asymptote, life becomes so horrible. And it keeps you both close friends separate. Now, you say, oh, I don't like the vertical asymptote. Because I was getting close to my friends from the other side, but it caused me to be separated from them. Ash is walking to the north. You are walking to the south. Then you never reach to each other. And that's the thing which I said, the story which I said, I'm going to write it like that. I say X, which is going to be Kelvin, is walking towards 2, which is my vertical asymptote, but Kelvin is looking at the bigger numbers. For example, from -2, 0, the direction of the X is this. In this direction, X is going to get bigger. X is going towards, it means that Kelvin is walking towards 2 from that direction. However, my function is this 2x minus 4. I know that I can show this with the concept of the limit to show that if they reach each other or not, then I say what happens? Kelvin is going all the way y. This is going to plus infinity. It goes to minus infinity. And I notice Kelvin is going all the way down to the south pole, which means that the limit of that function, when Kelvin approaches to that from that direction, goes to minus infinity. And essentially, that's the definition of the vertical asymptote. It doesn't matter if Ash is walking from right to left, or Kelvin from left to right, they are never going to reach each other. They are going, one is going to the North Pole, the other one going to the South Pole. So far away, yes. So, yes, both limits define the vertical asymptote. So we need both. That's right. Both of them. Guys, yes. Yes, please. Guys, when you just go to the higher years in the calculus, you are going to expand on the concepts of the limit. At this stage, we need only this. To see that, we can use it to define the vertical asymptote. Okay, any questions so far? Yes,
What is the x arrow 2 plus notation? What does that represent?
this one?
Just like the whole notation.
The whole, in this notation, the minus or plus on this?
No, just like the x arrow plus.
The x arrow, it means that x is moving towards 2, but from, when you see, here you see the smaller numbers, instead from right to left.
Would a question like ask us to give that kind of notation?
The vertical asymptote, and use that definition to explain it.
I see. Okay.
That's right. Now also we're going to talk about the horizontal asymptote. Okay, any questions so far? Ash and Kelvin, did you enjoy your ride on that plot?
Yes. It was solid.
Memorable?
Very.
Yes. You mean this? 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 What minus means? This? This? This one means? Oh, no, 2. X goes to 2. Yeah, there is no minus. Just x goes to 2. Thanks. No question, guys. That is fine. Now, I give you 30 minutes break, 1 minute break, then we move on to the asymptotic behavior on the horizontal level. Let me erase. Sorry, guys. Calvin and Ash, sorry, I'm just going to erase you both. Who's going to Quebec? I love that city.
I don't.
You're going to Quebec?
Yeah.
Oh, I love that city.
Me too.
Oh my God, I wish I can come back there once more. Are you from Quebec?
Yes.
Oh, you're from Quebec City.
Yeah, outskirts of Quebec City.
Oh, good for you. That's a lovely place. I have been there only once.
Oh, you should go more often.
Yes, that's the plan. Hopefully by this coming summer,
Yes, for sure.
I'll go to the Quebec City again. Okay, now, guys, now go back to our right. Now, I need one more volunteer to have a right. Let's now use Michelle for that right. Now, guys, look at Michelle from this perspective. Look, this is Michelle. Let me introduce you to Michelle. Michelle is standing there, guys. This is Michelle. Michelle, this is guys. Now, look at this. Michelle is standing somewhere between anywhere along the x-axis. And Russell is thinking to himself, can Michelle have that kind of freedom to walk along any direction? He said yes, as long as he is stuck to walk along the x-axis, that's going to be totally fine with that. Huh? Now, we say that if that's going to happen, let's see what happens. Imagine Michelle is running so fast along the x-axis, and it goes towards this direction as fast as she can. She runs towards positive direction of the x. Means that within half an hour, Michelle is going to see, for example, number 1 million plus 1 million along the x-axis. Tomorrow, if you imagine Michelle has had good lunch, she keeps running along the x-axis until tomorrow morning. And tomorrow morning is seeing 1 trillion, for example, along the x-axis. The number is going to get so high, then I'm going to say while Michelle is running towards the x, it is going towards plus infinity, means that the number is increasing so fast. Now, I'm going to write the same thing, f of x. You can also write f of x here. You do not need to just write the function itself, because f of x is this function. Either you can write the right side, or you can write the left side. It doesn't matter. You see that when Michelle is moving towards that line very fast, and I'm just going to introduce that notation here, the limit, because we are looking at extreme behaviors. The behaviors that are not normal. They are happening just along the x real line. Now, what happens in that case? We see that the limit means the function, the value that Michelle is going to see for the value. For example, if Michelle is at 1 million along the x-axis, what is the value of the function at y? Imagine that here, your x is going to be 2 million. What is the value of f of x? You take 1 over 2 times 2 million minus 4. Very small, huh? If it becomes 3 million, then it gets even much smaller. 1 trillion, Angelique. 1 over 2 times trillion minus 4. Oh my God. It is incredibly small. Then we assume it's going to be 0 because it's so small. Then we say that the limit of the function, when x goes to infinity, means x is getting bigger and bigger and bigger and bigger, it becomes 0. The same thing also for the left side. Now, for this example, Michelle was walking towards right. Now she decides to just walk towards the left. The same thing, I can write the same thing here and say that when x is going to minus infinity, means that Michel is moving along the x-axis, but towards the most biggest numbers, which is minus, which means that it becomes minus infinity, minus a million, minus 2 million. Then we say that, what is the value of the function when Michel is going towards minus infinity? Again, it becomes close to 0, huh? You put, for example, here 1 over 2 times million minus 1. Becomes 1 divided by a huge number. For example, Prayash, imagine that I found $20. I found $20. Yes, 22 cents. If I divided 1 over $20 and I distribute the amount here, how much do you get? At least, let's say $1. But if I get $1, I distribute between the population in Toronto. How much every person gets? Almost nothing. You have $1 divided by the population in Toronto, a huge number, means that almost nobody gets anything. Then as a result, we say that 1 over a huge number, it actually becomes what? Becomes 0. That's the second definition. That becomes my first definition, the second definition. Then now, guys, please listen, Alexandra. Now, you see that. Now, this time, the value of the function becomes 0. We say that. Then, as a result, I'm going to write it a little bit here. Let me change the color. Then we say that f of x equal to 0. F of x is essentially y. We say that y equals to 0. Y equals to 0, which line is this? Y equal to 0 is the x-axis. You remember that from level 3? The equation of the x-axis is y equal to 0. The equation of the y-axis is x equal to 0. Then when x goes to plus or minus infinity, when f of x goes to 0, we said that y equals to 0 is going to be horizontal asymptote. We said that y equal to 0, then is horizontal asymptote. Because as the function, you move along the x-axis, you see that it becomes y becomes smaller, smaller, and smaller. Okay. Now, Michelle, did you enjoy your walk along the x-axis?
Yeah, I did.
Do you have any memory along the way that you want to share with us?
Not really, no.
Okay. Now, then what we did so far, before we just move on to solve some examples, the thing that we did, first of all, we defined how to reciprocate a linear function to get a rational expression. That was the first thing that we learned. The second thing that we did was this. The denominator of the rational expression that we have created, if it goes to 0, it gives you the vertical asymptotes of your function. Yes? Yes? The second thing, also, thank you. The third thing was that we learned that in order to show the vertical asymptote, we have to satisfy these conditions. It means that if x is equal to 2 is your vertical asymptote, the left and right behavior of the function, which you show that by limit, should always go to infinity. If it doesn't go to infinity, it's not the vertical asymptote. And the last thing we talked about, the horizontal asymptote. We said that what happens with the reciprocate of the linear function, if x goes to infinity, we see that if x becomes bigger and bigger and bigger, your y becomes smaller and smaller and smaller, that eventually it leads to 0. Then as a result, we are going to draw this conclusion that for a reciprocate of a linear function, y equal to 0 is a horizontal asymptote. And it has to satisfy these two conditions. Then, within one sentence, today, we learn the asymptotic behavior of a reciprocate of a linear function. Now, before we move on to solve some questions, any questions so far from you? Yes, Michelle.
I don't really understand how you count the horizontal asymptotes, like how the very point on the ground.
We are just going to do one example, but look at this.
Okay.
For example, if that's f of x, we can plot, actually that's the purpose for the exercise which we are going to do after a break, is this. Imagine that. I can create a kind of a table, and I say that if this is going to be the x, and if it's going to be my f of x is 1 over 2x minus 4. Then I'm just going to give some values to this. For example, if I give 0 for x, then I say, okay, it's going to be minus 1 over 4. Then if I put 1 for the x, it becomes 1 over 2 minus 4. It becomes 1 minus 2. And you can continue the same process. Then you say, okay, what happens if I give, for example, 2,000? Then what happens? It becomes 1 over 2 times 2,000, Michelle, minus 4. Which is essentially becomes 1 over, imagine, 3,996. Can you put that in a calculator to see how much do you get? It becomes 0.00.
Oh yeah, it's like
How many zero do you get?
like it doesn't even say. The type is 0.25 times 10 to the minus 5.
10 to the power, okay. Minus 5 will be bigger than that. Can you see this? Oh, e to the power, okay. 2.5, yes. Becomes 2.5 times 10 to the power minus 4. You see that you get smaller and smaller when it comes to the value of x. Then as a result, you say, okay, why should I bother? Then I say that then x is going to infinity, as x has become bigger and bigger and bigger, then my f of x is getting smaller and smaller and smaller, which means that f of x becomes 0. Then this one becomes my horizontal axis. And actually, that's the plan that we are going to do in a second after we take 1 minute break. But that's a good question. Now, any questions, guys? If no, please go to the handouts that you have. Okay. Go to page number 149. Page number 149. Yes. Okay, spend 1 minute on this, different parts. Try to connect the solution which is written there for you to connect it with the things that you have done. Then we just do this together. Another example. Exercise example number 1, the function is 1 over 2x minus 1. Okay. Guys, essentially, when you look at that example, you see that lengthy description of the thing that is going to happen. It asks you, for example, part A, state the domain, part B, describe the behavior, describe the end behavior. We do not talk about the sketching of the graph because that's what we do then with the calculators. But for the first two parts of the question, look, the thing that we learned here, how is that going to simplify when we answer this type of the question? First of all, for part A, it's asking you what is the domain of this function. What is the domain? That's the question. Who got the domain? It's an easy practice now. Yes, yes, Melina. That's so true. Thank you. You look at the basement, and as you remember from level 3, you see that 2x minus 1, which is going to be the denominator of that expression, should not be 0. Then I'm just going to solve this for 0. Someone has given you an expression, an equation. You have no choice except to solve it. So it means that x equals to 1 over 2. What does it mean? It means that if you substitute x equal to 1 over 2, it sets the basement of your building on fire, and that's why you have to avoid it. Then as a result, when it comes to define the domain of f of x, I write it like that symbol. I say that then I'm going to introduce a set of numbers, which means that x is always a real number. However, I know that x should not be equal to 1 over 2, because if this is 1 over 2, it sets the whole building on fire. And that's how I define the domain of this. Yes, Laura? Isn't that beautiful? Yeah. Now, as Alex said, one slide gives you lemon. You make a lemonade. Now, you have something which causes the basement to go fire. We are just going to benefit from it and define what? The vertical asymptote, which is going to be the part of, I should say, B and C. It means this. For the part B, let me erase this and write it there to be that the camera also can record it. Yes. Yes, please, please. Now, for part B and part C, that it asks for the end behavior and the behavior of the function, we focus on the vertical. This is what that's for the singular points. Our singular points, which I got it from here, from the first part, is x equal to 1 over 2. This one, what does it mean? This one is a disaster. Because if you plot the function, you get a behavior like this. Like in that case that we had Ash and we had Calvin over here, they couldn't reach to each other. They were getting separated. Then this point, which is the 0 of the denominator, it defines for me what? The vertical asymptote. How can I just explain the vertical asymptotic behavior of this function? I say that x goes to 1 over 2 from the left, which means that I put the minus sign on there. It's a kind of a symbol. It says that, for example, Calvin is walking towards 1 over 2 along the x-axis, but he is standing behind it, is walking towards it. Then, if x is going to 1 over 2 from the left, then you say that f of x I put a limit there, becomes what? F of x jumps all the way to the infinity or minus infinity. From 1 over 2, if you close to this, it goes to minus infinity. Why? Because imagine if the plot resembles to something like this, but it's going to be 1 over 2. Let me plot it here. Okay, that's the point which we had to avoid it. 1 over 2. I'm going to show you like this. This is 1 over 2. The function is plotted, then it behaves like this. If, for example, Calvin is walking along the x, but approach to 1 over 2 from the left, means x goes to 1 over 2, with the minus sign there, it's a symbol that says that Calvin is going to point 1 over 2 from behind. There are two symbols. No, just stick to that one. That if this is minus, it goes behind. If I said that previously before, just stick to that definition. Because there are two different notations for that. In different books, I stick to the one which you have on your textbook. In different books, they have another notations which I gave you. If this is 1 over 2 with the minus sign on top, it means that you're standing behind that point based on the textbooks that you have. But in another textbook, you find different notations. I stick to the textbooks that you have. If this is minus 1 over 2, it means that you are standing behind of 1 over 2 and you are getting close to it from behind. Then, if that happens, you get close, you get close, you get close, you fall down. Then you are going all the way to the South Pole that you see minus infinity at the lowest cost of that thing. Then it becomes minus infinity. It becomes my first definition of this. For the second definition, I said that, okay, imagine now Medina is going to 1 over 2, but from the right side of 1 over 2. I put the positive, which it means that Medina is standing ahead of 1 over 2. It's a little bit bigger than that. Then it means that if Medina is there, Medina is going towards, for example, this is Medina, is walking towards 1 over 2 from its right side, and she knows that. She has to stick to the plot. She cannot just jump from the plot, walk along the x-axis. She has to walk along the black line. She goes, she's going all the way to the plus infinity. The value of y becomes so huge, then that's why we say that f of x, we said that the limit of f of x becomes plus infinity. These two definitions that we have here, it represents the end behavior or the asymptotic behavior, vertical one for that function. However, that's the same answer on page number 150. But remember, instead of describing them in sentences, sentence after sentence, I use these two symbols that we're going to use that in the next year also. It makes it much easier. Now, the very last part of it, how much time do we have? 10 minutes. The last part is that imagine that you are walking along the x toward as what we shall be. For example, if x becomes too much, the function is this, 1 over 2x minus 1. If x becomes so huge, that's what we X is not 1, X is not 2, Lauren. X is 1 trillion. It's too much. You plot it into that function, becomes 1 divided by 2 times 1 billion minus 1 trillion. Then when you divide 1 over a huge number, it becomes a very, very small number. Then it means that the limit of this function. When f of x, when x you plot, you put infinity over the x, then you get 1 divided by something so big, which means that it becomes almost 0. Then this is become the definition that y equals to 0 is the horizontal asymptote. This is essentially, that's in one sentence that what described, it's essentially almost half a page description of this one. Page number 150, part C. When x goes to minus infinity or plus infinity, you see that there is almost half a page of the verbal description just for the thing that we have written here. You see that by using this symbol, the concept of the limit, you save half a line, half a page of description using the words. And here you are for that example. You see that? By simply writing that in 1, 2, 3 lines, using just the symbol notations of the math, we solve 2 pages of exercise 11. It depends on you. You can just, for the text, you can use either of these methods. Use the concepts of the limit, or describe that x becomes small, x becomes large, what happens to the function. Okay, a productive day so far. What time is it now? 2:53. Trouble, is it good everything? Danielle, is it good everything?
Yeah.
How about you, Angela?
Yes, great.
I'm so glad to hear it. Yes. Both vertical and horizontal, your end behavior. Because you're looking at the function's behavior when everything becomes extreme. What happens at the end of the universe?
Okay. So you put like all 4.
That's right. End behavior is, that's a good version. End behavior is both vertical and horizontal asymptotes. It means that what happens to the functions, how the function behaves when everything becomes extreme.
Right.
Like Elon Musk, he became the richest man. It means that how Elon Musk behaves asymptotically when x, which represents his wealth, becomes so huge. He's going to donate it to the United Nations. I heard it on the news today. He's going to sell these stocks if they can give him a plan how to just eradicate hunger. Okay. Now, I think it's good to stop here. It's good to stop this part of the lesson here. Now, guys, please everyone go to page number 154. Page number 154, you are going to see an extremely interesting stuff. But before that, guys, please, page number 154, exercise number 3, all of it. Please do this and bring it next session to the class. However, before we leave, it's not a bad idea to do one thing, also learning the symbols that the text would also use them. How much time do we have? 5 minutes, huh? Okay, look at part number 1, exercise 1, page number 153. When you learn these contents by using the limits, these kind of tables, it's gonna become like an easy game. Look at this. It gives you a function, part A, for example. F of x is 1 over x minus 2. It asks you to fill out the chart. Look at this, how easy it is. When you learn those stuff, you see, oh my god, this is stuff, are you joking? Look at this. It says that x goes to something, f of x goes to what, for example. Guys, if x goes to 2 plus, and also you have the plot, imagine the same plot that we have almost. If x goes to 2, guys, everyone please look at the board in case when you just want to do the activity, you do not feel it's get stopped. Ariana and Alexander, look at this. For this function that we have, if x goes to 2, but a little bit bigger than 2, for example 2.1, how about f of x goes to what? For example, you come with an example. You say that 2 plus 1 becomes like 1 over 2.1 minus 2. Becomes 1 over, for example, 0.1 becomes something. You put it in a calculator. How about if x goes to 2 minus? It means that you find the value of the function, but x is going to be a little bit smaller than 2. For example, 1 over 1.99 minus 2. You put this in the calculator, you find the value. These are essentially all the things that we did, but in a very, very elementary way. How about plus infinity? X goes to plus infinity, like this case. X becomes all the way to a large number. Means that, for example, 1 over 1,000,000 becomes almost what? So x becomes too much. How about you see on the y-axis? 0, that's right. And the same thing for minus infinity. X becomes all the way to a huge number. Again, what you see over the blue line is going to be always also a 0 number. These two essentially, guys, instead of using this table, we came to show this method that f of x, when x goes to infinity, goes to 0. That's why we call that y equals to 0 is a horizontal asymptote. Then, next session also, you're going to talk more about this, solve more problem. But please remember, page number 154, exercise number 3, you do this. And today was essentially, you put the building block also for your calculus course, which is going to be for next year. Now, today was a very important session. If you have no questions then, I'll see you all next session. And enjoy the day. Yes.
Fashion shows whether
Wait. Oh, now we have to